All right, so let's start this lecture. So last time we talked about Hamiltonian analysis. Well, last few lectures we talked about Hamiltonian analysis about ADM formalism, and also we have talked about Ashitaka variables to prepare the quantization. So now there is one topic we left that we didn't talk about. We always that's about so-called boundary terms in the Hamiltonian formalism. Yeah, I always talk about. I will always mention that, and in the calculation, I said I talk about later. But now we have to get it back. So let's talk about boundary terms. In Hamiltonian. Okay. But I will only talk about it briefly. So I only give you the scheme how to calculate these boundary terms and what's the result. I'm not going to go to the detail about it, but there are of course a lot of references to study it. And one reference is a book by Ward. GR. Okay, the book by Ward. It is a reference for boundary terms. So let me consider this as the boundary term. So remember that when we derive this Hamiltonian, so let's come back to the ADM formulation because we got less terms in Hamiltonian. So in ADM formulation, remember the Hamiltonian is linear combination. It's a linear combination of Hamiltonian constraint and diffeomorphism constraint. Okay. However, as I said before, we have ignored a boundary term. We all the time throw away boundary terms. So which means you have to add a certain boundary term. Yeah. So it's on the boundary of the sigma with a boundary term. Okay, and this is so sigma is a 3-manifold. So partial sigma is a 2-dimensional manifold. Therefore, you have to integrate in a 2 form on the 2-manifold. So B is a 2 form. So it collects all boundary terms. Boundary terms we ignored in the calculation. So there are 3 resources of the boundary term. Firstly, from the Lagrangian, there is a Gibbons-Hawking boundary term. So which means in the 3+1 decomposition, you have to also study Gibbons-Hawking boundary term. So which means it reduced to certain boundary terms in the Hamiltonian formulation. Secondly, when you study the Hamiltonian, the Hamiltonian 3+1 decomposition and calculate the Hamiltonian for the bulk term of Einstein-Hilbert action, you also have to do a lot of integration by parts, and it also gives some boundary terms. So therefore, it has 2 resources. So firstly, from Gibbons-Hawking. Yeah, in the Lagrangian level, and secondly, boundary terms from integration by parts. Okay. So there are 2 resources. Of course, and you should be in principle you are able to compute this boundary term from these 2 resources, but this is not the way we are supposed to. It's not the way that I'm going to do. I'm going to perform some. Well, there's another logic to get this boundary term. Of course, that's the same boundary term. So the other logic is to consider Hamilton's equation. Consider Hamilton's equation Q Ij equals to delta H delta P Ij Qij. Okay, consider this guy, this Hamilton's equation. But then you see that you have to be able to compute this quantity, right? So this quantity has to be well defined. So which means well, these has to be well defined, right? So which means here it is the variation derivative of h with respect to all those variables. And you have to, so they has to be well defined. Suppose without this boundary term, these are not going to be well defined. The reason is that to do this variation of the Hamiltonian, you are going to get boundary term. You are going to get some other boundary term, right? Just like you make variation with respect to Einstein-Hilbert action and get Einstein equations, you have to incorporate the boundary term. Well, in case your manifold has boundary, you have to incorporate the Gibbons-Hawking boundary terms to make the variational principle well defined, because otherwise you will get some other boundary term. The job of the Gibbons-Hawking boundary term is just to cancel the boundary terms coming from variational principle. Well, in the Hamiltonian formulation, this boundary term should do the same job, right? Otherwise, your Hamiltonian, your Hamilton's equation is not well defined anymore. Okay, so let's consider the variation of h. 3x. Okay, and let's rigorously produce this variation of h. And then, of course, it will be a linear combination. So this is the total derivative of h. It will be a linear combination of all the variation of the variables. So the coefficients for delta Qij, I will call it t, and for the other, for delta Pij, the coefficients I will call it s. Yeah, so both of them, both t and s, they are functions of p and q, and of course they are also relates to n and ni, all the dynamical variables, all the variables. Okay, but in this calculation, to compute the variation of h, you have to, you are going to get some boundary terms, right? Because some pq in h, p and q are in derivatives, are inside the derivative. You have to do integration apart, move the derivative to the other side, and so you get delta q and delta p from outside, right? In the outside. So which means you have to add some boundary terms. I mean, which means from this variation, you are going to get some additional boundary terms. So let's call the, let's consider the boundary of sigma is S2. Well, and maybe I just call it partial sigma. So there are previous boundary terms, delta B, because I mean, you do variations and you have to also vary the entire Hamiltonian, you have to vary boundary terms. And then you have additional boundary terms coming from the variation of the bulk term. So boundary terms, so this is the boundary terms. From delta okay, so well, just like your previous experience on variation of action, if you do variation and try to write the functional in this form, the variation of the functional in this form, you definitely extract lots of boundary terms, because you have to do lots of integration by parts. Yeah, and each of the integration parts give you a boundary term. Yeah, this is the origin of this delta B prime. Okay, and now in order to make the Hamilton's equation well defined. Okay, for example, so to make delta H delta Qij and delta H delta Pij well defined. It's you have to let me put it together in order that is R well defined. You must have delta B plus delta P prime equals to 0. Okay, those boundary terms must cancel. Otherwise, I mean, it's the variation just not well defined, because you have some additional term you are not going to, you cannot extract functional derivative because it's at the boundary, and yeah, you will find it is difficult to extract the functional derivative. Well, I mean, the reason why is not, okay. You may wonder if you compute the functional derivative of delta B with respect to delta Q. If you compute delta B with respect to delta Q, well, things you can, yes, maybe you still can compute it, but it will be a delta function, three-dimensional delta function integrated on the surface, right? And that's singular. So that's why the variational principle is not well defined. So here in the box, so you get three-dimensional delta function, yeah, and integrate in 3 dimensions. But on the boundary, you get three-dimensional delta function integration in 2 dimensions. This is singular. Okay, so which means, well, that's the reason why we say that the variation of H is well defined, so that you must have all the boundary terms cancel. Yeah, that's, well, remember that's exactly the argument for Gibbons-Hawking boundary term. Okay, so now we get. So you see, this is a new way, a different way to compute this delta B. Okay, you just solve this equation, and because this delta B prime you can compute from considering variation of the bulk term, which you can compute this delta B prime. So once you compute delta B prime and this delta B, you know this delta B. Okay, and that's the way. So from this means this equation, you obtain delta B and B itself. Yeah. Usually in this way you can at least you can find delta B, and then you can find also B, so that give you the right delta B. Okay, so once you get this B, you know that the total energy, the total Hamiltonian, total energy of the gravitational field, energy so this is actually not only gravitational field, it's everything inside space-time. Inside space-time. Inside space-time. Namely gravity plus all the matter. The total energy is the total Hamiltonian. E3x C plus I Ci plus the boundary term. Okay, so this is the total energy. So this formula. So before when we derive this formula, we only consider pure gravity. We didn't take into account matter. But suppose even we consider all kinds of matter coupling, this expression is not going to change. The only thing changes if you couple matter is the expression of the Hamiltonian constraint and de Morgan constraint. So this C will be C gravity plus C matter. And similar for Ci. C matter. Okay, so you will get, and suppose you consider matter coupling and do the Ci. Consider the Hamiltonian analysis for gravity coupled to matter, then you will get the different, you get some additional matter term in your Hamiltonian constraint and diffeomorphism constraint, but this expression is not going to change. Yeah. And because as we know that on the constraint surface, Hamiltonian constraint and diffeomorphism constraint is 0, so therefore H is the total energy is just the boundary term. B, suppose you are able to compute this B, and then this the resulting B is just the total energy. So total energy of everything inside spacetime, including gravity and matter. So here you can see that the energy, once you have considering coupling energy, well, once you consider the energy of gravity or energy of gravity with matter, once gravity is involved, your energy is non-local, right? So it means that gravity energy is non-local. Yeah, the energy of gravity or everything coupled to gravity, you can only talk about the total energy. You are not able to talk about the energy density. You cannot point to a space-time point, ask about the energy at this point. Yeah? You can only ask about the total energy of the entire space-time, because your total Hamiltonian is just a boundary term. You have no sense of energy density for once gravity is involved. All right. Okay, so now let me, of course, here I'm not going to show you explicitly how you compute this boundary term B, but I'm going to give you one example and the result of that example. We consider asymptotically flat spacetime. For example, Schwarzschild spacetime that we learned before. Can you still hear me? So it shows that the network is not stable. Can you still hear?
Yeah.
Yeah.
Yes.
Yes.
Okay. Let's consider asymptotically flat spacetime. Well, I mean, in the asymptotic flat time, asymptotic flat space-time, you can find a asymptotic flat coordinate. For example, in Schwarzschild coordinate, you can find this TR theta phi coordinate, which is asymptotic flat, namely the metric written in that coordinate reduced to flat metric if you go to asymptotic infinity. So say let's say the tx1, tx2, well, tx1, x2, x3 is asymptotically flat coordinate. Namely g mu nu in that coordinate reduced to eta mu nu if as r equals to square root x dot x goes to infinity. So this is the definition of asymptotic flat coordinate. And then you can, so this coordinate defines a 3+1 decomposition because you have time and space. You know what is time and what is space in this coordinate. And then this the Hamiltonian in this setup, in this 3+1 decomposition, you can compute the boundary term, for example, in the case of asymptotic flat spacetime. And by the way, and G mu nu reduced to eta mu nu in the asymptotic flat region, it is a boundary condition for the system, right? And it imposes certain kind of boundary conditions, and using that boundary conditions, you can simplify these two form B. So here is the result, and the resulting Hamiltonian is called ADM energy. It's called ADM energy. H equals to limit, because here the boundary is at infinity, r equals infinity, and then this integral of over the boundary. This is S2, but S2 is a function of R. So because you have your three-dimensional space, so you can draw a lot of two spheres enclosing your space. Yeah, so suppose this is your space sigma, and you go to infinity. Infinity is your boundary, and then you just draw two spheres, S2, with a certain radius r. This is r, and you have lots of spheres. You can draw different spheres with different radius, yeah, and so this in this formula you are integrating over these two spheres. And the integrand is following: I j equals 1 is 3 q I j I j. So the first term is xj. So this is jj. It's the trace of q. Q is the same as, well, it's a spatial metric. I have to remove this. And also there is a determinant of h. This is the induced metric on the sphere. Sigma is the coordinate on the sphere. So h is induced metric. Induced metric on this S2. Okay, and sigma is the coordinate on S2. So this formula, so this is the so-called ADM energy. So this is basically the boundary term computed in the case of asymptotically flat spacetime. That's the result. So I skip the derivation. Probably on the book by Ward, you got some derivation for this formula, or otherwise you can just Google and try to find formulas, try to find expressions, the derivations toward this formula. It's not so hard to find. Okay, and since we have learned Schwarzschild spacetime, there are lots of different kinds of asymptotically flat spacetime, including Schwarzschild, Rathenau Nordstrom, Kerr, and Kerr-Newman. They are all asymptotically flat spacetime. Specifically for Schwarzschild spacetime, if you can perform this computation, you just apply this Schwarzschild coordinate. You just apply the Schwarzschild coordinate and get the components of the coordinate, and you get this qij and qjj. You just compute derivatives, right? And it's very easy to do. And the result is this. Space-time, your ADM Hamiltonian, the result is just the m, yeah, and the parameter in the metric, which is the mass of black hole. Yeah. So at the very beginning, when I introduced Schwarzschild spacetime in the previous class, I just say I tell you that there is a free parameter m in the metric, right? And I didn't tell you. So at that time I claimed that this m is the mass of black hole, but I didn't tell you why it is the mass of black hole. So here it is why, because if you compute the total energy, total ADM energy of the spacetime, you find the result is this m, and the only thing inside, well, the only thing inside the spacetime is gravitational field, and is this black hole, and then you interpret this parameter m is mass of the black hole. All right, so this is the very brief discussion of the boundary term. Okay. So now let's come back to the Ashtakar's formulation, and then sorry.
May I ask a question? Yeah. We know that the energy momentum tensor for the matter field is localized even in so from the argument.
No, it's not. It's not localized. No? The energy momentum tensor in general relativity, everything is all the. There's no, if you couple matter to gravity, you don't have local energy. So you have local energy for matter field is because you didn't couple them to gravity. You just consider space-time, you just perform matter field on space-time. You don't couple with gravity.
Okay.
Right. So of course on Minkowski space-time you talk about well, in ordinary field theory. In ordinary field theory, you talk about the matter densities and the energy densities of all kinds of matter field. But you can talk about it because you don't couple it with gravity. Also, in any other curved spacetime, you can perform field theory. You consider field theory on the curved spacetime, and then you talk about energy momentum tensor, and that's it include energy density. But you can talk about it. It's only because you didn't really couple matter field with gravity. Yeah, you just consider matter field on a given spacetime. You are not coupling matter field to gravity. So here the statement is that once you couple, really consider it rigorously, really do things rigorously, which means matter excite gravities, which means matter couples to gravity, then you have no sense of local energy density. So everything, all the energy has to be a boundary term. It's non-local. Right. So that's really the speciality of gravity, yeah, because you have a diffeomorphism invariant theory. Okay, so I think that should solve your problem. Okay, so let's so we finished the boundary term, and yes, so let's come back to the Ashtakar variable and prepare for the quantization. So let's this part is called preparation of the loop quantum gravity quantization. Of loop quantum gravity quantization. So this is the procedure we have to do before really come to the quantum theory. So what is exactly we do to prepare the loop quantum gravity quantization? So it is a lattice regularization, lattice discretization of the smooth field. Of your smooth field, the Ashtakar connection, and the densitized flux. So the canonical variable in Ashtakar's formulation is this the Ashtakar connection, one form, and the densitized flux. And this lattice discretization is the analog of lattice gauge theory. Lattice gauge theory. Because maybe most of you don't have much experience on lattice gauge theory. So the story for lattice gauge theory is following. So in the non-abelian gauge theory, so you can, of course, in your quantum field theory class, some of you must have learned that you can do perturbative calculation, compute correlation functions perturbatively or scattering amplitude perturbatively on the continuum. But suppose you want to understand non-perturbative questions, and especially for non-abelian gauge theory, this is very important because non-abelian gauge theory, you have asymptotic freedom. It means that you can do perturbative calculation only in the high energy regime because it's asymptotically the non-abelian gauge theory is asymptotically free in high energy, but becomes strongly coupled at low energy. Yeah, becomes strongly coupled at low energy. Yeah, so which means if you really want to consider the low energy effect of non-abelian gauge theory, you have to go beyond the perturbative regime, consider the non-perturbative regime of the non-abelian gauge theory. And this is very important because what we observe in nature, it is always low energy effect. It's always low energy effect. You don't really observe quarks and you don't see those free quarks because this is really existing at high energy. What we actually observe in experiments are pion, mesons and pions and those composite particles coming from QCD. Okay, so which means that for non-abelian gauge theory, you have if you want to understand the low energy effect, you have to get rid of the perturbative calculation because it's only valid near the asymptotic free regime. You have to come to the non-perturbative calculation of the gauge theory. Then of course, you can see that when you consider strongly coupled phenomena, it becomes very complicated. And then the strategy in non-abelian gauge theory is that you put the gauge theory on the lattice. Yeah, you discretize this gauge theory. The theory is not, you don't define this gauge theory on the continuum space-time, but define it on the lattice.